In an electrical power system, understanding the difference between a multiple bonded system and a single bonded system is crucial for ensuring safety and proper operation. Leakage current, an unavoidable phenomenon in most electrical installations, plays a significant role in how these systems behave. Leakage current, typically caused by insulation imperfections, transient voltage surge suppressors or TVSS, and electronic devices, flows through equipment, grounds, and other metallic paths. This current must ultimately return to the source of power, which, in this case, is a generator system. Generator breakers are equipped with ground current sensing circuits that monitor the neutral and phase currents to calculate the ground current. In a multiple bonded system, neutral and ground are connected at multiple points, such as the paralleling gear in each generating unit. This arrangement allows normal neutral currents to split and return to the generator through both the neutral conductor and other parallel metallic paths. Consequently, leakage current flows through multiple paths, resulting in a high ground current value that is displayed at the generator breakers. Consider a scenario where a generating plant is initially installed with neutral ground bonding jumpers at the paralleling gear and each of the 4 generating units. The collective ground current flows across the neutral ground bonds in the paralleling gear and at the generators, with each generator displaying a current value of approximately 65 amps. This is because the normal neutral currents from the building split at the paralleling gear and return to the generator on both the neutral conductor and other parallel metallic paths to the generator neutral point. Now, let's examine what happens when the multiple neutral ground bonds at the generator units are removed, effectively creating a single bonded system where the neutral and ground are bonded only at the paralleling gear. In this configuration, the normal neutral current flows solely on the neutral conductor. The expectation might be that the ground current would decrease significantly, potentially even approaching zero. However, the ground current value remains approximately 65 amps per generator. This seemingly counterintuitive result occurs because the leakage current from the building equipment, grounds, and metallic paths still flows across the paralleling neutral ground bond to the neutral conductor and then back to the generator neutral. As a result, the current flowing back on the neutral now includes the current injected from the neutral ground bond to the paralleling gear. This combined current is then interpreted as ground current between the paralleling gear and the generator. To summarize the behavior of these two systems, firstly, in a multiple bonded system, neutral and ground are bonded together at multiple points, including the paralleling gear and the generating units. Normal neutral currents split and return to the generator on both the neutral and other parallel metallic paths, and this system allows leakage current to flow through multiple paths, resulting in a higher ground current value displayed at the generator breakers. Secondly, in a single bonded system, neutral and ground are bonded together only at the paralleling gear. Normal neutral current flows on the neutral only, and leakage current flows from the building equipment grounds across the paralleling gear neutral ground bond to the neutral conductor and then to the generator neutral. The key takeaway is that removing the multiple neutral ground bonds at the generator units does not necessarily eliminate the ground current. Instead, it concentrates the leakage current path through the remaining neutral ground bond at the paralleling gear. This means that the normal neutral current now includes the current injected from the neutral ground bond, and this combined current is detected as ground current between the paralleling gear and the generator. It's essential to understand these dynamics when designing and maintaining electrical power systems to ensure proper grounding, minimize circulating currents, and prevent potential hazards. Understanding the nuances of neutral ground bonding is critical for managing ground currents and ensuring the safe and efficient operation of electrical systems. Now let's delve deeper into the individual components and principles that govern the behavior of multiple and single bonded systems. We will start with a foundational understanding of grounding and bonding, then examine the role of leakage current, and finally analyze the implications of different bonding configurations on ground current flow. Grounding is the process of creating an intentional low impedance path to the earth. This path allows fault currents to flow back to the source, tripping over current protection devices such as circuit breakers or fuses. Grounding serves two primary purposes. Firstly, It protects personnel from electric shock by providing a low impedance path for fault currents, and secondly, it limits voltage rise during electrical disturbances, preventing damage to equipment. Bonding, on the other hand, involves connecting all non-current carrying metallic parts of an electrical system together to create an electrically conductive path. This includes equipment enclosures, metal conduits, and other metallic structures. The purpose of bonding is to equalize the voltage potential between these parts, minimizing the risk of electric shock. When a fault occurs, the bonded metal parts provide a low impedance path for fault current to flow back to the source, facilitating the operation of overcurrent protection devices. Now let's consider leakage current, which is an inherent characteristic of electrical systems. Leakage current is the small amount of current that flows through the insulation of electrical conductors and equipment. It is caused by imperfections in the insulation, capacitive coupling between conductors, and the presence of electronic components that generate harmonic currents. While leakage current is generally small under normal operating conditions, it can become significant in certain situations, such as when insulation is damaged or when nonlinear loads are present. In a multiple bonded system, the neutral and ground are connected together at multiple locations. This creates multiple parallel paths for current to flow back to the source. When normal neutral current flows, it will split between these parallel paths, with some current flowing through the neutral conductor and some current flowing through the ground conductors. This can lead to circulating currents in the ground system, which can cause voltage drops and interference with sensitive electronic equipment. Furthermore, in a multiple bonded system, leakage current can flow through multiple paths, resulting in a higher overall ground current. This can make it difficult to accurately detect fault currents and can increase the risk of nuisance tripping of overcurrent protection devices. In contrast, a single bonded system has only one connection between the neutral and ground, typically located at the service entrance or at the generator. This eliminates the multiple parallel paths for current flow and reduces the potential for circulating currents in the ground system. In a single bonded system, normal neutral current flows primarily through the neutral conductor, and leakage current flows from the equipment grounds across the single neutral ground bond to the neutral conductor, and then back to the source. This configuration simplifies the ground current path and makes it easier to detect fault currents. However, it is important to note that the single neutral ground bond must be properly sized to handle the expected fault current. If the neutral ground bond is too small, it can become overloaded during a fault, leading to a voltage rise in the ground system and increasing the risk of electric shock. Now, let's examine the specific scenario described earlier, where a generating plant was initially installed with neutral ground bonding jumpers at the paralleling gear in each of the 4 generating units. This configuration represents a multiple bonded system. When the neutral ground bonds at the generator units were removed, the system was converted to a single bonded system with the neutral ground bond located only at the paralleling gear. The observation that the ground current remained approximately 65 amps per generator after the removal of the multiple neutral ground bonds can be explained by the fact that the leakage current was still flowing through the single neutral ground bond at the paralleling gear. This leakage current, combined with the normal neutral current, resulted in a significant ground current reading at the generator breakers. The magnitude of the ground current depends on several factors, including the amount of leakage current in the system, the impedance of the ground conductors, and the location of the neutral ground bond. In some cases, it may be necessary to implement additional measures to reduce the ground current, such as installing filters or improving the insulation of electrical equipment. In summary, understanding the differences between multiple and single bonded systems is essential for designing and maintaining safe and reliable electrical systems. Multiple bonded systems can lead to circulating currents and higher ground currents, while single bonded systems simplify the ground current path and make it easier to detect fault currents. The choice between a multiple bonded system and a single bonded system depends on the specific application and the requirements of the electrical system. In some cases, a hybrid approach may be appropriate, where multiple neutral ground bonds are used in conjunction with other grounding and bonding techniques to achieve optimal performance. In any case, it is important to carefully consider the potential impact of different bonding configurations on ground current flow and to take appropriate measures to mitigate any potential risks. The National Electrical Code, or NEC, provides detailed guidelines for grounding and bonding electrical systems. It outlines the requirements for size and grounding and bonding conductors, installing ground electrodes, and connecting equipment to the ground system. Adhering to the NEC requirements is essential for ensuring the safety and reliability of electrical systems. The NEC Article 250 covers grounding and bonding requirements. It is crucial to consult the latest edition of the NEC for specific requirements related to grounding and bonding in different types of electrical systems. Let's talk about some of the practical implications of these concepts. Imagine you are troubleshooting a ground fault in an industrial facility. You notice that the ground fault current is significantly higher than expected. To diagnose the problem, you would need to understand the grounding and bonding configuration of the electrical system. If the system is a multiple bonded system, you would need to check for circulating current in the ground system. You might also need to measure the impedance of the ground conductors to identify any high impedance connections. If the system is a single bonded system, you would need to ensure that the neutral ground bond is properly sized and that there are no other unintended ground connections. In another scenario, consider a hospital operating room where sensitive electronic equipment is used. In this case, it is important to minimize the potential for electrical noise and interference. A single bonded system is generally preferred in this type of application because it reduces the potential for circulating currents in the ground system. However, it is also important to use shielded cables and to properly ground all equipment to minimize electrical noise. Now let's delve into the mathematical aspect of ground current, bonding impedance, and leakage current calculations. While a precise calculation is complex and requires detailed system parameters, we can establish a basic framework to understand the relationships. Firstly, let's consider the concept of impedance. Impedance is the total opposition that a circuit presents to alternating current. It's a combination of resistance, which opposes current flow, and reactance, which opposes changes in current or voltage due to inductance and capacitance. The impedance of a grounding conductor, for example, directly affects the magnitude of fault current that can flow through it. A lower impedance grounding conductor allows for a higher fault current, which in turn facilitates faster tripping of other current protection devices. Now let's relate this to Ohm's law. The simplified version of Ohm's law, voltage equals current times resistance, can be extended to alternating current circuits by replacing resistance with impedance. This gives us voltage equals current times impedance. Using this relationship, we can estimate the ground current if we know the voltage and impedance of the ground path. For example, if we have a 120 volt system with a ground path impedance of 1 ohm, the ground current during a fault would be approximately 120 amps. In reality, the impedance of the ground path is much more complex and includes the impedance of the grounding conductors, the ground electrodes, and the soil. Next, let's examine the role of leakage current. Leakage current is the current that flows through the insulation of electrical conductors and equipment. It is typically caused by imperfections in the insulation, capacitive coupling, and harmonic currents. The magnitude of leakage current depends on the voltage, frequency, and the insulation resistance. In a multiple bonded system, leakage current can flow through multiple paths, increasing the overall ground current. To calculate the total leakage current, we would need to sum the leakage currents from all of the sources. However, this is often difficult to do in practice because the leakage current is typically distributed throughout the system and is difficult to measure directly. Furthermore, bonding impedance plays a crucial role in determining the distribution of ground current. The impedance of the bonding conductors affects how the ground current splits between different paths. Low impedance bonding conductors will carry more current, while higher impedance bonding conductors will carry less current. To analyze the current distribution, we can use Kirchhoff's current law, which states that the sum of the currents entering a node must equal the sum of the currents leaving the node. By applying Kirchhoff's current law to different nodes in the ground system, we can determine how the ground current is distributed between different bonding conductors. In summary, ground current, bonding impedance, and leakage current are all interconnected and play a crucial role in determining the behavior of grounding and bonding systems. Understanding these relationships is essential for designing and maintaining safe and reliable electrical systems. While precise calculations can be complex, a basic understanding of Ohm's law, Kirchhoff's current law, and the concept of impedance can help us to estimate ground current and analyze the distribution of current in the ground system. Now, let's discuss some practical steps to minimize ground current and improve the performance of grounding and bonding systems. Firstly, minimizing leakage current is essential. This can be achieved by using high-quality insulation, regularly inspecting and maintaining electrical equipment, and avoiding overloading circuits. Using shielded cables can reduce capacitive coupling and minimize leakage current. Secondly, optimizing bonding impedance is important. Ensure that all bonding conductors are properly sized and installed according to the NEC requirements. Use short, direct bonding paths to minimize impedance. Avoid creating ground loops which can increase circulating currents. Thirdly, implementing ground fault protection is crucial. Ground fault circuit interrupters, or GFCIs, can detect small ground fault currents and quickly disconnect the circuit, preventing electric shock. Ground fault protection systems can be used in industrial and commercial applications to protect equipment and personnel. Fourthly, performing regular ground testing is essential. Ground resistance testers can be used to measure the resistance of the ground electrode system. Bonding impedance testers can be used to measure the impedance of bonding conductors. Regular testing can identify potential problems before they become serious. Fifthly, using isolation transformers can minimize ground current. Isolation transformers provide electrical isolation between the source and the load, preventing ground current from flowing between them. Isolation transformers are commonly used in sensitive electronic equipment and in medical facilities. In conclusion, understanding the principles of grounding and bonding is essential for ensuring the safety and reliability of electrical systems. By minimizing leakage current, optimizing bonding impedance, implementing ground fault protection, performing regular ground testing, and using isolation transformers, we can minimize ground current and improve the overall performance of grounding and bonding systems. It's also important to remember that the NEC provides detailed guidelines for grounding and bonding electrical systems. Adhering to the NEC requirements is essential for ensuring the safety and reliability of electrical systems. Remember to consult the latest edition of the NEC for specific requirements related to grounding and bonding in different types of electrical systems. Grounding and bonding are fundamental aspects of electrical safety and system performance. Proper understanding and implementation are crucial for preventing electrical hazards and ensuring the reliable operation of electrical equipment.